Okay, so that's an equation which is given by the SQA, but it's only one situation. It's just for lens coatings. Still hasn't answered the question why we get purple when you look at a high quality lens, and you actually see this on mobile phone lenses now, the quality is so much better. Why does it appear purple? Well, you're actually seeing two colors and you're missing out on one color. What color is in the middle of the spectrum? White? Middle of the white is the whole spectrum. What's in the middle of that white spectrum that goes through all of the, or green? Yeah, so green's in the middle. You've got red at the longer wavelength ends, and blue and violet at the high frequency, short wavelength ends. So the lens coating's tuned and designed to work best with wavelengths of green light. So if that's trying to reflect green light, then just go back a stage. If that's trying to reflect green light, which wavelengths are not going to be, are actually going to be reflected a little bit better because we're cancelling out all the green? What's left over, Hanberger? Red and blue. Put red and blue together and you get purple. So, or magenta, to give it its correct name. Okay, so so the reason that you're getting that purplish hue is because the red and blue light add together. In reality, a lot of the more expensive lenses have various extra coatings to try and reduce the reflection of other wavelengths as well as just the green. So you'll get multi-coated lenses, and that's why they're all very expensive. Okay, moving on. If I meant to bring in some bubble solution, but if I had, could make some soap bubbles, and you would see this sort of effect, lots of different colors. But where do the different colors come from? And if you have a soap film in a hoop like that, why do you get that gradation of colors as you go down through the hoop that's got the soap? So again, we've got to think about what the phase changes are and what the optical path difference is. So we're looking for constructive interference here. So we've got the external reflection coming out. Are we going to get a phase change there or no phase change? Should be getting slicker at that. Phase change of pi because it's going into more dense. Okay, it carries on through a thickness and then reflects back. Phase change on the far side? Nope, because it's off a less dense, but back to air on the other side of the soap bubble. So phase change here, no phase change here. If you're wanting the two to come out in phase, what's the return path got to be to give you them back in phase? What would the thinnest be to give you them back in phase? Half a wavelength. So what would the actual thickness D have to be in terms of wavelength? And over lambda, not over 2, but lambda over 4, because it's there and back. And because it's in the refractive index n, then it's lambda over 4n. It looks the same as the lens coating equation, but it's doing a completely different job. Here you're getting constructive interference because you want reflection of that particular bit of light that you're seeing that's giving you the soap bubble. But because you've got a difference in the reflection phase changes, then you've got the same equation for the distance there, but you've got a different effect. Okay, so that's with the soap bubble. Why do you get the different colors? That's because as the soap bubble drops down, it gets wider and wider. It drains away from the top, and that's eventually why soap bubbles pop. So as it gets wider and wider, going down like that, then the wavelength gets longer and longer. And so you start with blue at the top, and you progressively go down to get red further down at the bottom there. So that's what you're seeing there. Now, the thing is, why is there a dark region at the top? Just before it pops, if you illuminate a soap bubble with white light in a ring like that, that will appear absolutely black, even though you've got white light shining on it. There's absolutely nothing reflected. Okay, going to leave you with that one to think about. Last one is if you got oil on water. Again, you get reflection. There's a distance there that you've got. You'd have phase change of pi on the top. No phase change of pi depending on the refractive index of the oil compared to the water. It's generally a higher refractive index of oil than water. So that's, and with the different angles, you're getting different wavelengths will be reflected. And lastly, the DVD surface. The reason that DVDs work is they have little pits or holes dug into them in the optical surface, and it's that slight phase difference there, optical path difference in the surface of the disc, which results in either constructive or destructive interference, and that's what's carrying the binary information, the ones and zeros that make up your digital audio or digital video. The reason that Blu-rays discs can carry more information and fit more stuff on is the wavelength is much smaller, so the physical dimensions of everything is smaller, so it basically shrinks it all down. So that's why Blu-ray was a big advance compared to normal optical. Okay, so you've got two equations from all of this, one for the wedge fringe, one for the lens film coating. The SQA have this annoying habit of coming up with examples that don't fit into those two equations. So what you've got to do is firstly think, are you looking for reflected light to be constructive or destructively interfering? What are the phase changes at each boundary? And what's the path difference that you're dealing with? And then remember that any reflection, the distance that you've got has to go there and back. So you'll have to half the actual optical path difference to give you the thickness. So fair bit in that. What we're now going to do is try some questions on that, just to give it a practice. I'll leave that up as a note